Boa tarde a todos, sejam todos bem-vindos a mais uma live do canal do Museu Joias da Natureza. É um museu que tem um ideal: divulgar, difundir e educar a população, a sociedade nas ciências naturais, principalmente nas geociências, que são ciências tão incríveis, né? E uma delas que nós estamos tentando focar são as ciências planetárias, astronomia, enfim. Quero agradecer a todos que participam do canal, que estão inscritos no canal. Peço para que se inscrevam no canal e divulguem as nossas lives, que ficam gravadas, tá, no YouTube. Eu também gostaria de agradecer ao nosso parceiro, o IPBio, pelo apoio que tem desenvolvido as lives do museu ao longo desses anos. E tenho um enorme prazer e alegria de, quando faço lives, estou em contato com os maiores cientistas das suas áreas. E isso me enche de alegria, de orgulho também, poder compartilhar um pouquinho do meu conhecimento, que é pouco, mas do conhecimento enorme desses grandes cientistas. E hoje é mais uma live super especial. Nós tivemos na última live também pessoas maravilhosas, grandes cientistas. E dentro dessa área de crateras de impacto, que é um tema extraordinário, que envolve geologia, biologia, geografia, química, matemática, física, astronomia, enfim, é uma área fantástica. Eu trouxe agora um dos maiores pesquisadores de impacto do mundo, Dr. Christian KOEBERL. Thank you very much for your kindness. You accept this interview. E trouxe para fazer a mediação o maior especialista, o maior pesquisador de crateras de impacto do nosso país, um dos maiores do mundo também, Dr. Álvaro P, que é meu amigo querido e que já esteve aqui no canal algumas vezes, dando essa força, esse apoio. Então, para a gente começar a nossa live, eu gostaria que o Dr. Álvaro fosse o mediador e fizesse a condução da live, primeiro se apresentando, para quem estiver nos assistindo, e depois fazer a apresentação do nosso convidado e também que ele fizesse uma apresentação breve da sua carreira, o porquê do interesse em crateras de impacto, dessa temática tão importante, vista hoje que nós estamos em Marte, estamos querendo ir para Marte. Acabou de chegar a amostra da Lua aqui, né? Da Lua não, do asteroide Bennu, né? Então, assim, enfim, tem muita coisa acontecendo na astronomia e a gente fica feliz de estar com esses dois grandes geocientistas aqui. Então, por favor, doutor Álvaro, a palavra é sua, para depois que a gente terminar essa apresentação, a gente começar a apresentação do Dr. Christian. Por favor, Álvaro.
Muito obrigado, Paulo. Quero agradecer o convite, a honra aí de estar novamente aqui com vocês no canal do Museu Joias da Natureza, um prazer enorme. E um prazer ainda maior de estar aqui com o meu amigo Christian KOEBERL, um amigo dileto e também um parceiro de pesquisas aí de longa data, que já visitou o Brasil várias vezes, conhece algumas das nossas crateras de impacto, né? E tem colaborado bastante aí conosco ao longo dos anos. Para apresentá-lo, eu vou discorrer muito brevemente sobre a carreira dele, porque ele tem um currículo extenso, né? Então, eu vou destacar alguns pontos aqui. Ele é professor titular da Universidade de Viena, na Áustria. É austríaco de nascimento, fez uma boa parte da sua carreira na Áustria, mas também em outros países. Ele se graduou e fez o doutorado em astronomia e química na Universidade de Graz, lá na Áustria também. Foi chefe do departamento de pesquisa litosférica da Universidade de Viena e foi, durante 10 anos, diretor-geral de um dos melhores museus de história natural do mundo que eu conheço e recomendo a todos, que é o Museu de História Natural de Viena. Como diretor-geral do museu, ele dinamizou extremamente o museu, tornou moderno, interativo. Então, realmente é um trabalho muito formidável que merece ser conhecido por aqueles que tiveram a oportunidade de visitar Viena. Fica bem no centro da cidade e, de fato, vale muito a pena. Bom, ele já foi cientista de visitante de um grande número de instituições no mundo, como o Lunar and Planetary Institute e o Johnson Space Center da NASA, ambos em Houston, né? A Carnegie Institution em Washington, a Universidade de Witwatersrand, na África do Sul, o Dartmouth College, nos Estados Unidos, a Open University, no Reino Unido, e várias outras, né? tem muitos prêmios ao longo da sua carreira, vou destacar alguns. Ele é membro titular da Academia Austríaca de Ciências, tem o nome de um asteroide que foi dado em homenagem a ele, o asteroide 15963 KOEBERL. Recebeu a medalha de maior honra, digamos assim, da área de pesquisa de crateras de impacto, que é a Behringer Medal da Meteorite Society. Ele também é fellow da Meteorite Society. E, mais recentemente, em 2022, ele foi agraciado com a Cruz de Honra na arte de ciência e cultura, na primeira classe, pelo governo austríaco. Então, destacando, você vê que é uma carreira científica realmente de monta, né? Foi editor de muitos periódicos científicos, eu destaco aí o Geological Society of America Bulletin, onde muitos anos ele foi o editor científico-chefe, né? Tem 23 livros de sua autoria ou de coautoria, 15 que ele foi também coeditor, e, acreditem vocês, 520 artigos publicados em periódicos, além de mais de 700 resumos e outros tipos de publicações em congresso, né? Então, vocês vejam que é uma carreira realmente extremamente brilhante, destacada aí. Por isso mesmo, justifico o que o Paulo falou, que o professor Christian KOEBERL é um dos cientistas mais destacados do mundo nessa área. Bom, eu vou parar por aqui, porque o currículo é longo. Christian, I'm trying to introduce you, but there are so many things that I can tell about you, and I think we better hear what you have to tell us. So I think the word is yours. You can please proceed.
Well, thank you very much, Álvaro, for the very nice introduction. I could hear a few words that sounded familiar. Unfortunately, I do not speak Portuguese, so I'm sorry about that. But I heard asteroid and metal and this and that. So thank you very much for the invitation to speak here. I understand that you have already heard from Álvaro and from some other people who talk about impact craters. So this will be my take on impact craters, and I'm going to try to be reasonably popular and general about it. And so what I'll do now is I'll share the screen, and I'll start with my presentation, which should last about, I don't know, 40 minutes or something like that, somewhere on that order. And then I understand there will be questions, and then maybe Álvaro and I can discuss a few things, and we'll see how it goes. So let me just do the sharing. I hope it works. Fortunately, we do see the technical aspects of the PowerPoint and not only the presentation. So now you should see my screen. Can you see it okay?
Yes, it's okay.
All right. So the title of my presentation is Meteorite Impact Craters on Earth, Cradle of Life and Mortal Danger. And that might sound a little bit strange, but first I'll be talking about impact craters on Earth, a little bit about how they look like, how do we know that they're impact craters, so how do we detect that a geological structure is of impact origin. And then I'll talk a little bit about what we know or think we know about impacts and the early Earth, and then particularly about today, kind of where are we today? What is the danger? You know, we look at the moon and other bodies, and here is actually the moon. Can you see the moon?
Yes.
Okay, good. So we're okay. So here you see the moon, and the moon is covered with impact craters. And so, of course, the moon is our neighbor in space, our closest neighbor in space. And what distinguishes the moon from the Earth is that the moon does not have an atmosphere. So even small bodies that hit the surface of the moon will make a crater. And the second thing that the moon doesn't have, or not anymore, is active geological processes that modify the surface of the moon. whereas the Earth has all of that. And this is why craters on the Earth are not as visible. They are not as well preserved as on the Moon. But of course, we are subjected to the same cosmic bombardment as the Moon is. And all the craters that you see on the Moon here, there are the same number, actually even more per square kilometer, so to say, on the Earth, because the Earth has larger gravity than the Moon. But before going into these details, what I would like to do is just say 2 or 3 words, or use 2 or 3 slides, rather, to talk a little bit about history. How do we know kind of certain things, and how do we get to what we know today? And this is why in the upper part of that image that you see here, there is a drawing. It's an old drawing. It's over 400 years old. It is by Galileo Galilei, the famous Italian astronomer, who in the early 1600s was the first person that we know of, at least, to use a telescope, small telescope that he built himself. The telescope was invented shortly before in what is now Holland by a guy who normally makes glasses for people who don't see well, named Hans Lippershey. And Galileo in Italy had heard about that there is a way how to use some lenses to magnify things. And he built his own telescope, and he looked at the Moon, for example. He also looked at Jupiter and Venus, and he was the first one to see the phases of Venus, and he was the first one to see the 4 big moons of Jupiter. But when he looked at our Moon, what he saw, and it was patient observations, and that little drawing is a little exaggerated, but it shows that he understood that on the surface of the Moon, there are craters. They are not mountains, but it's the inverse. It's a bowl-shaped depression. And he knew that because he followed the shadows. And this is what you see in the middle of that little image here. So Galileo was the first person to ever conclude that the surface of the Moon is covered by lots and lots of craters. Now, that doesn't mean he knew how these craters had formed. We know from Earth, and this was what influenced a lot of people back then, that a lot of craters are volcanic craters. And of course, being in Italy, there have been a lot of volcanic craters. For example, near Naples in southern Italy, there is the Campi Flegrei, and maybe right now even you hear in the news that there is some danger that there might be an eruption coming up again. But so this was known for a long time, and there's lots of craters there. So a lot of people over many centuries were believing that the craters on the Moon, and therefore craters elsewhere too, all formed by volcanic activities. Well, you can't blame people too much for this opinion, because let's go and look at the next picture here. Now here, this is an old woodcut, slightly colored now, of course, which shows the fall of a meteorite in 1492. It's a long, long time ago, at a place which back then was Germany, called Ensisheim. Now they adjusted the borders a little bit, and it's in the so-called Alsatian area of northeastern France bordering Germany. But there was a big piece of rock that fell from the sky. Now, meteorites are rocks falling from the sky. But where do they come from? How did they get there? And so for a long time, people were thinking that they could be either something similar to hail. You know, hail are these icy droplets that fall out of some clouds, and nobody shoots them up first, they just come down. And so some people were thinking, well, Meteorites are similar to hailstorms. They're just rocks that fall from the sky. And others were thinking maybe there was a volcanic eruption far, far away, because you find rocks coming from volcanic eruptions that even float on the ocean for hundreds of kilometers away at distances. So it was entirely possible. And for the longest time, people were thinking that meteorites are actually coming out of the Earth's atmosphere. Now, of course, the view, and not just the view, but the knowledge back then was that all you have in space are some planets. There's Mercury, there's Venus, there's Mars, there's Jupiter, there's Saturn. That's what people knew about. And then later in 1781, Uranus was discovered. But that's all people kind of knew about. Nothing else was known. And the conclusion that people who were thinking about where meteorites come from, they took in the 16th, 17th, 18th century was, well, it has to come from the Earth somehow because the space between the planets is empty. But this was what people knew back then. There was nothing known between the planets. The first minor planet or asteroid was actually discovered in 1801. And shortly thereafter, in France, in 1803, there was a large meteorite shower that fell down from the sky. And it was so spectacular that the French Academy of Sciences sent a scientist from Paris to investigate this. This guy was Jean-Baptiste Biot, shown in this picture here. And what he did was something very new. He interviewed a lot of people, hundreds of people. Where did you see the rocks falling? Which background to the sky? And so he used the technique called triangulation. And with that, he was able to kind of backtrack where these stones that were falling from the sky actually came from. And he was more or less the first, or one of the first, to conclude that they had to have come from outer space, from outside the Earth's atmosphere. So basically, it was only in the beginning of the 19th century, that's not very long ago, that scientists realized that there's actually rocks falling from the sky, from outside the Earth's atmosphere. And mostly it was the small rocks that we know as meteorites. But back then, nobody had ever seen a big impact of something bigger. But of course, people realized, and it was only in the 20th century, even more recent, that it's possible that even larger pieces can fall from the sky and they can make craters. Now, let's go and look at a few bodies. Here's just a reminder that tells us when you have these meteors or shooting stars that you see, they are high up in the atmosphere. They're out when a small extraterrestrial body hits the atmosphere, then it will ionize the atmosphere. The atmosphere, the air will glow. So it's not the body itself that you see, it's the ionized atmosphere. And this lasts about a second or two maybe, and then it's gone. But this happens in about maybe 60 to 120 kilometers above us in the atmosphere. A really big object called a fireball, I'm sorry for the German in the diagram here, but a fireball that you see on the left side, this may come down to maybe 40 kilometers, but it's also possible that an object survives because it's slowed down by the atmosphere, and then a small chunk of rock falls down on the surface of the Earth, and that's a meteorite. But if there is a real big one, maybe bigger than 50 meters in diameter, then it's not slowed down enough in the Earth's atmosphere anymore, and it hits the surface of the Earth with very, very high speed, many kilometers per second, and that is what then makes a meteorite crater. So, okay. Now let's look at the moon again. So here we have lots and lots of craters. As I said before, even the smallest objects may make a crater there because there's no atmosphere to absorb or slow down small ones. So there's no fireballs, there's no shooting stars over the moon because there's no atmosphere. But other planets have similar things. So in the upper left here, we see the surface of Mercury, the innermost planet in the solar system. It also doesn't really have an atmosphere, so it looks like the moon, covered by craters. On the lower image here, we see a radar image of a crater on the surface of Venus. Venus has a very dense atmosphere. Venus is about the same size as the Earth, a little bit smaller, but not much. But it has a very, very dense atmosphere, so we cannot see the surface. So we need radar. There have been spacecraft to use that and do that. And so lots of craters have been found, several hundred of them. Not as many as on the surface of the moon or on Mercury, simply because there is an atmosphere there, and it so absorbs all the smaller objects. While the big reddish object on the upper right, of course, is Mars. And we see lots and lots of craters there on Mars as well. Mars has a very thin atmosphere. And so there's lots of craters there, going way, way back also. Well, even now, we have spacecraft in the orbit around Mars, and there have been some images that were sent back where a very fresh crater that you didn't see, for example, here, that area had been photographed in 2009, but when it was photographed in 2011, oof, there's a new crater here. Not a very small, not a very big one, maybe it's a few tens of meters in diameter, but that shows us that on the surface of, say, the moon or Mars, even we can observe these days the formation of new craters. So that's something interesting. Now, then we have, as we know now, the asteroids, the minor planets, mostly orbiting the sun between Mars and Jupiter. And there is thousands and thousands and thousands of them that we know. There's a number of large ones. The largest one in this particular picture is only 130 kilometers long, so it's not particularly large. The largest one we know is almost 1,000 kilometers in diameter. But there are many, many, many small ones. We now know the orbits of about 1 million of those asteroids, of those minor planets. But when we look at these pictures, there's a few of them that have been visited by spacecraft, and that's why we have these photos, where you see two things. First, they're irregular. They're not spherical because they're too small to be spherical. And the other thing is they are covered by craters themselves. So there's constant collisions going on between these objects in space, in between these small objects. And then, of course, we go in the outer solar system. Well, we know the big planets, Jupiter, Saturn, Uranus, and Neptune, they don't have a solid surface. So there is nothing where any record can be kept. But they have moons. And those moons, they show plenty of craters. We see a moon even on an icy world like Europa on the upper left. Titan is a moon of Saturn on the upper right. It has an atmosphere, even it's the only moon that we know of that has an atmosphere, but there's craters. Mimas, a moon of Saturn as well, is a huge crater in the middle. There are many, many others. Phoebe, another moon of Saturn, again, craters everywhere, basically, so to say. Well, craters, how's it look on Earth? Well, here is a very well-known impact crater on Earth. It's the so-called meteor crater, also called Beringer crater, after the person who studied it first in great detail at the beginning of the 20th century. This crater, which happens to be in the desert in Arizona, not very far from the city of Flagstaff, it's not very far from the Grand Canyon either, and it is an almost circular feature. It's a little bit angular, but almost circular, about 1.2 kilometers in diameter and about 250 meters deep. And this was studied, as I said, the first time beginning of the 20th century. Just earlier, a little bit before, at the end of the 19th century, people found meteorites all the way around this crater. And it was iron meteorites. But interestingly enough, they named it not after that crater feature, which at that time, of course, was not called meteor crater, but Coon Butte. So So lots of coons, you know, these nice animals with the big tails. They were obviously living there. But the meteorites were named. In the upper right corner of this picture, you see a little canyon. This is the so-called Canyon Diablo, and this is how the meteorites were named after. But then, in the beginning of the 20th century, a guy named Daniel Barringer was studying that crater, and he drilled it and did all kinds of things. And it took a while, actually a couple of decades, before, and he thought it was, you know, a meteorite impact, but it was very difficult to understand how it formed, because what he thought was that underneath the crater floor, there's the big meteorite that made that crater. Well, that was because he did not really know the mechanics of crater formation, and nobody knew at that time. And it was only later, in the second decade of the 20th century, that the first studies were made that more or less indicated that to form a crater of this size, you don't need a 600 meter diameter meteorite. You only need a small object, maybe 50 meters in diameter. So the crater is about 20 times larger than the impacting body was. And so no wonder you didn't find big meteorites, you only found little fragments that were left over. And why is that? Because of the huge amount of energy that is involved in making such a crater. I'll come back to that in a few minutes. So this particular crater was very, very important for our understanding of how craters like that formed on Earth. Now, in the meantime, of course, we know more craters. We have identified more craters more recently. But I have to make clear that it was not until the 1970s or 80s, really. So really not that long ago, 40, 50 years ago at the most, that people accepted, geologists accepted, that a lot of small crater structures on Earth actually formed by impact and are not volcanic. Because the problem is there's many other geological processes on Earth that can form craters. It's not just volcanoes. It's also wind features, it's karst features, it's collapse features. It's a variety of other features. So most craters on the Earth's surface are actually not formed by impact, unlike the moon, where most craters on the surface are impact craters. So it is not easy to identify impact craters on Earth. And the general geologist, at least until the 1970s or 80s, never encountered an impact crater, never heard anything about an impact crater. Nothing was taught in universities and so on about impact craters, because it was a very rare, very, very rare phenomenon, and most people never knew anything about it. So here we have three craters that are relatively small. On the bottom one, there's one in South Africa. It's very interesting. It's about the same size, the same diameter as this meteor crater in Arizona. But it is not as crisp, as clear as that crater was. And in fact, you don't find on the surface anything that really tells you it's an impact crater. You have to drill down. Only in 100 meters depth below that little lake that's there did some impact-related evidence show up. And so it's no wonder that people were kind of suspicious about impact craters. What the evidence is, I'll talk about in a few minutes again. But so, and then it's interesting to see. So this crater obviously has been subjected to erosion. The crater rim is not as crisp anymore, as sharp anymore. It's kind of rounded. It's filled in partly. So this is the fate of craters on Earth. Erosion takes a toll. Or also the other possibility is that erosion somewhere else fills up these craters and covers them up, and then you don't see much on the surface anymore. And what's the really interesting thing is this particular crater here in South Africa is only 5 times as old as Meteor Crater in Arizona. Meteor Crater is about 50,000 years old, and this one is about 250,000 years old. So within a geological, very short time period, craters on Earth start to disappear, which makes it, as I said, difficult to recognize them. Here's one in Libya. You don't see much anymore. There's a little bit of eroded hills. Here's one in Chad, similar thing. There's no crater rim left. Here's one in Australia. Now that's an interesting case. When you look at this nice ring of hills that you see there, in the aerial photograph on the lower right and the satellite picture up there, most people will think, oh, that's the crater. No, it's not. That is what we call the central uplift. In the middle of a larger crater, rocks from greater depth come up. They kind of move up. Many people will have seen these videos of a milk drop that comes up in the middle of when a drop goes into the milk. And so it's similar with the rocks. You know, there's something coming up in the middle. In the actual crater, you can still see a little discoloration that is much, much larger, that fills about half the image, in fact. So in this case, hundreds of meters have been lost from the surface, and only a little bit of the eroded leftover of that central uplift remains. That crater is about 140 million years old, which is not that old, in fact, geologically speaking. Now here we have one that geologists know well, and that is, again, the remnant of a central uplift of a larger crater. That crater used to be about 300 kilometers in diameter. Now what we see is just a fragment, a part of the central uplift, maybe about 60, 70 kilometers in diameter. So in that case, about 10 kilometers of rock have been lost from the surface. So what we see here was when that crater formed very deep below the surface. This crater is 2 billion years old. So it's one of the oldest ones we know about on the surface of the Earth. Well, considering that the Earth is 4.5 billion years old, that's interesting. We barely have anything that is older than that. But because there are hardly any rocks left that are that old. Most of the rocks on the surface of the Earth are much younger. So we've seen simple craters that, you know, like meteor crater, that are basically bowl-shaped depression. We call them simple craters. And you see in this diagram, there's some fractured rocks, some melted rocks, some so-called brecciated rocks, which are ground up and re-cemented rocks. Or on the bottom, we see this Gosses Buff crater from Australia again, where we just have the remnant of the central uplift, and on the right side in the diagram, we see the central uplift, and we see that here in the middle, there's that kind of mountain that comes up, and if you assume that the whole crater rim has been weathered away, has been eroded away, and all the filling is gone, and all you see is rocks that used to be deeper than where they are now, and this is what we have there as a leftover part of a central uplift. So this is how they look like. Where do they come from, these objects that make craters? Well, I've said there's a lot of small bodies between Mars and Jupiter, but a lot of them also, many of them, we know several tens of thousands, over 30,000 by now, they are called Earth-crossing asteroids. So some of them get close to the Earth, they can cross the Earth orbit. And here we have some orbits plotted of the ones that are larger than a kilometer in diameter. So only the large ones are plotted here. And that's already plenty enough. Of course, most of that is empty space, but occasionally it's possible that two of those bodies meet in space, and then we have an impact. How do we know anything about impact processes? What happens during an impact? Well, nobody has seen an impact, fortunately. You know, they're not as common. They're less common than some volcanic eruptions, but there are some things where we can learn from. One possibility where we learn from is man-made explosions, real big explosions like nuclear explosions. Here we see a photograph on the upper right of an explosion that happened in 1963 in the desert of Nevada, US. And on the bottom, you see the remaining crater afterwards. So these can be studied. Or in a laboratory, there's a NASA laboratory where we can accelerate little rocks very fast and hit the surface, like in this picture. And what we see, very interestingly, for example, in this picture, is even though the impact happens at an angle, the resulting crater is circular, and the ejecta material is also circular. This is made with a very fast camera, these images. And the impact happened, I think it's a 30-degree angle to the surface, which tells us it's interesting because what we see here the angle of the impact makes no difference. The resulting crater is always circular. This was what puzzled people at the beginning of the 20th century, because they said, well, if all these craters on the moon are supposed to be of impact origin, why aren't they elliptical? Well, because what we see, this is what also Barringer learned after a while, why is there no big meteorite underneath the crater floor? Well, you don't need it. And here is what happens in a very schematic way. You have a very small object that hits the surface of the moon, the Earth, Mars, whatever, with very, very high speed. And what we are looking at here are speeds of 10, 20, 30, 40 kilometers per second. So all of those of you who still remember a little bit of physics from school, you may remember there was an equation for what is called kinetic energy, the energy of movement. So you have a moving body that moves very fast. The energy that is released when that body, in this case, hits the Earth or the moon is half the mass, but you multiply that with the velocity squared. So we have a huge velocity anyway. You square that number. So the amount of energy that comes out here is enormous. So a huge amount of energy being released. And this is what does two main things here. You see in the image called B on the upper right, that there's like waves going into the ground. This is what changes the shock wave. This changes the parameters or the rocks and the minerals, so you can actually recognize that there was an impact, because this is a pressure that is so much higher than what happens in normal geological processes, like a volcanic eruption. That is so much higher that it makes a big difference. And the second thing is, then, because of the huge amount of energy, we're looking at something that is very similar to an explosion. And so it clears out a large crater. And when you look at the upper left and the lower right images, it's a small body that causes a very, very large crater. And the diameter ratio is something like 1 to 15 to 1 to 20. So the resulting crater is on the order of 20 times larger than the impacting body. Depends a little bit on the composition, if it's mostly rock or has some iron in it or so, but that's the general case. So that's what we have with these large craters. So how do we identify that something is an impact crater and not a volcanic crater? Well, things like a circular outline, that there's a rim, that there's a central structure, that there's gravity anomaly, magnetic anomalies, and so on. Well, this indicates there's something interesting there, but it's not clear proof of an impact origin, because karst structures or volcanic structures are also circular. They also have a magnetic or a gravity anomaly. So that doesn't help us much. It just alerts us maybe to an interesting structure. So what we really need to look at is we need to look at the rocks. And this is because there's a difference, as I said, between the moon and the Earth. On the Earth, a crater structure that's formed by impact is not as clearly preserved and as clearly visible as on the moon, where there is no volcanic processes, by the way, going on for the last billions of years anyway. So, but on Earth, so we need to look at the rocks. And in the previous picture I showed you, there is some shock wave that goes into the ground. Well, that changes the mineral structure. And this is what we call study of shock metamorphism. So the minerals change in a way that is unique to impact and that we can detect. And also, of course, if in the resulting breccias or melt rocks or classes even sometimes, we find traces of meteoritic material within that crater structure or clearly related to the crater structure, that is evidence for an impact. But we have to be careful, because the impacting body, the asteroid, is relatively small compared to the amount of terrestrial rock that is altered and modified and molten. So we only find very small amounts of meteoritic material mixed in with mostly terrestrial material. So again, it's not an easy thing to do. So what are the lines of evidence for shock metamorphism? So there is shock metamorphism that you can see in a hand specimen, like here, the so-called shatter cones. There are craters in Brazil I worked on with Álvaro Crósta, where we found shatter cones. And that was evidence that they actually formed by impact and not by anything else. So these are clear evidence, but they're, again, not easy to find. And also, to the layperson, look at the picture in the lower left. These look similar, but they're formed by a very different geological process, by a sedimentary process. So you need to be a little bit of an expert to kind of see what is a real shatter cone and what is not. Also then, if you have a microscope, a real good microscope, and you make thin slices of some of these rocks, breccias and melt rocks, you may find quartz grains in there that look like this here in some of these images. You see these lamellae, these lines that go through the quartz crystals. These are clear evidence of shock. This means these quartz crystals have been subjected to a very high pressure for a very short time. So this is the definition of a shock. A shock is high pressure, but it doesn't last very long. But the pressure is so much higher than when you get in, for example, volcanic eruptions, that it causes these interesting features in quartz grains and some other mineral grains as well. And again, geologists who are experts in this field, they can easily recognize these very nice so-called planar features. So they're straight, they're parallel to each other, and so on. So it's easy to see. I've already mentioned meteoritic components and impactites. This means you have to do very detailed geochemical analysis of very rare metals, for example, the platinum group elements, the PGEs. There's iridium, osmium, and other elements like that that are very common in most meteorites, but very, very rare in rocks on the Earth's surface. So there is a possibility, if you find high abundances of, say, iridium, that it has something to do with an impact. But again, you need to be, the laboratories are expert laboratories. There's very few in the world that can do it properly because it's a very difficult analysis. So what I'm kind of getting at is it's not easy, and not every, even an amateur geologist can easily detect if something is impact related or not. So it really needs some detailed studies. So all these studies have led us to identify, you see an Earth map and you see lots of white spots there. Those are impact craters that have been identified on the surface of the Earth so far, about 200 of them so far. Well, compared to the moon, there's nothing. But the problem, as I said, is on the Earth's surface, there's all these geological processes that help to obliterate, to make these craters go away or to cover them up. There's a very famous example, and this is one of them that kind of changed the minds of a lot of geologists. In 1980, there was a group of geologists led by a guy named Walter Alvarez from the US, who was studying the boundary between an age on Earth called the Cretaceous, it's abbreviated with a K, and the following Earth age called the Tertiary. And what they were looking actually for something else, but by chance, they were analyzing a thin rock layer between these two geological eras. And what they found in there was really, really interesting. They found a huge amount of these platinum metals in there, iridium, osmium, platinum, palladium, and others. And the only explanation for that huge amount was there was an impact somewhere. Now, we all know, and paleontologists all knew at the time, that the end of the Cretaceous is also marked by the disappearance of a lot of animals and plants on the surface of the Earth at that time, about 66 million years ago. The most famous group of animals that disappeared are the dinosaurs. So within a geologically extremely short time period, basically you can put a knife there in the rock record, and it was that short, all the dinosaurs disappeared. On the bottom you have dinosaurs, on the top you don't have dinosaurs. But dinosaurs were only one part. Over 70% of all living species disappeared at that time. So something huge was going on. And then people found these strange anomalies, these metal anomalies all over the world. Everywhere where there was one of these Cretaceous Tertiary boundary rocks, there was a signal. People had just not been looking about it before. And then a few years later, people found also these shocked quartz grains in the same level. Only there, not 5 centimeters above and not 5 centimeters below. Only that thin layer. And so then it was clear that there was a huge impact that had gone on somewhere. And it took 10 more years until the beginning of the 1990s that the location of that crater was actually determined and the crater was found and identified. It is now called the Chicxulub impact structure. It is partly on the Yucatan Peninsula in Mexico, and it was found to be about 200 kilometers in diameter. That is large. It's one of the largest craters on the Earth's surface that we know about. But why didn't people know about it early? Well, because younger rocks, this happened about 65, 66 million years ago, rocks that are younger, that were laid down since that time, covered it up. And you don't see anything on the surface. So you needed geophysical studies and drilling. There was a lot of drilling going on, first by the Mexican oil company, but then now scientific drilling as well. And there's a lot of scientific evidence that clearly links the rocks from that crater with these ejecta found at all these Cretaceous Tertiary boundaries in Italy, in Spain, in New Zealand, in India, in China, in Brazil, everywhere around the world you find those. So this was an enormously large impact. Here's an artist's representation of what might have happened. The asteroid that hit the surface of the Earth back then was about 10 kilometers in diameter. Well, that's large. And the resulting crater was about 200 kilometers in diameter. The crater is still there. There's a lot of effects, environmental effects, that resulted from that. Fireballs, huge winds, tornadoes, hurricanes. The burning ejecta were setting woods on the fire, but then there was a lot of dust going in the atmosphere, which kind of made the sun go away. There was nothing that hit the surface of the Earth for decades. This is how a lot of these animals died up afterwards. And then there was volcanism that was triggered by it, and greenhouse effects, and so on and so on. So this is one example of a huge impact that happened not that long ago in the geological record, but we also know of impacts that happened a long time ago on the Earth's surface. Here is another artist's impression of the surface of the Earth about a little over 4 billion years ago. The moon was still much closer. There were none of these big mare, these dark areas yet on the surface of the moon. They formed by impacts a little bit later. We knew the surface of the Earth had an ocean already back then. Impacts happened like here. And we have evidence for the first recorded, or the oldest preserved, to phrase it differently, impact evidence on Earth is here in South Africa. This picture, about 3.5 billion years ago, there's little spherules that were formed by impact, and we know a number of those, and those were also very, very large impacts. But only a very small percentage of the Earth's surface is preserved from that age. So the craters themselves are not preserved anymore. They probably will never be found. But a little bit of the material that was thrown out from these craters is left over, and that helped us, like through detective work, to find these impact remnants. Here's some pictures on the right side of these spherules and spheral layers. So, of course, this happened in the Earth history. And by the way, this is what I call also the cradle of life, because back then the Earth's surface got less sunlight than it did today, because the sun was a little bit weaker. So it was cool. So these impacts might have delivered warm places on the Earth's surface that helped with the development of simple primitive life. But today, when life is more complicated, we're a little more afraid of impacts than we praise them. So for example, in 1994, you see a photo montage of a comet nucleus that had been ripped apart by gravity interaction with this huge planet in the background, Jupiter. And one after the other of these little fragments of a comet nucleus hit the surface, or the atmosphere, I have to say, there is no solid surface of Jupiter. And here we see a remnant of that impact in the atmosphere. And we know this was a small body. It was maybe just a kilometer across, and it made this big kind of cloud in the atmosphere. And if we want to know how big that is, let's put the Earth in comparison there. So you see a small kilometer-sized impact makes an impact cloud that is as big as the Earth. So these little things have big effects, let's say it that way. And so I live in Vienna. Here's a picture of Vienna, and I superimposed the meteor crater on it. So if that would have formed back then there's actually an impact, and you see most of Vienna, that line that goes through it from the upper left to the lower right, that's the river Danube. And that is a small impact. And what is left over afterwards is that most of the central part of the city would be totally gone, and the rest of the city would be destroyed from that impact. And that was the impact of a 50 to 100 meter diameter object. So even these little objects that we don't even know the orbits of, because they can come out of blue sky, they can cause a huge amount of destruction. And so what can we do about it? What do we know about it? Well, I have a few slides here. I'm getting to the end of my presentation, another few minutes here. But so just in comparison, here's that big church that we have in Vienna, the St. Stephen's Cathedral, which is about 130, 140 meters tall. You see on the right picture, it would disappear in that meteor crater, but the object that made the crater was not even as big as a third of that St. Stephen's Cathedral. It's on the right side. Now, fortunately, impacts are not very common, but they do happen. And at the beginning of the 20th century, in 1908, there was a body, maybe 30, 40 meters in diameter, that entered the Earth's atmosphere and was mostly stony. It was over Siberia. And it didn't reach the surface of the Earth because it was ripped apart by internal forces in the atmosphere. We call that an airburst. So smaller objects explode in the atmosphere before hitting the ground. But the area that was destroyed, there was an expedition that got there almost 20 years later. You see the right image. 1927. A huge area of woods was totally destroyed, which is larger than New York City or Washington, D.C., and about 4 times the size of the city of Vienna, by the way. And that object didn't even reach the surface of the Earth. So if these things can be that destructive, well, what does that mean? Well, fortunately, something like meteor crater, and here again, excuse the German diagram, but basically shows on the bottom axis the diameter of the asteroid, 0.11 or 10 kilometers in diameter, and on the y-axis, on the left axis, says how much time between one impact of that size. Well, something like meteor crater happens every few thousand years on Earth. A bigger one, maybe a 1 kilometer diameter impact that makes about a 15, 20 kilometer diameter crater, maybe every millions of years. Fortunately, a Chicxulub-sized impact that would kill 70% of everything alive on the planet or more, only every maybe 100 million years. So, but even the small ones can be locally destructive. Some people might remember about 10 years ago, in 2013, there was a large explosion, again over Russia, in the area of Chelyabinsk, where a small meteorite asteroid fragment, only about 20 meters in diameter, exploded in about 20 kilometers altitude above ground, not an airburst. The shock wave, the airburst wave, knocked over walls, blew in windows in the middle images there. It injured about 1,500 people in the city of Chelyabinsk, which was over 60 kilometers away from the explosion place. So very far away, in fact, and even so much damage. Would that explosion have happened directly above a populated city, many people would have died. It was interesting because for that day, astronomers actually expected that there's a small object that you see in the green orbit here, in the bigger diagram, was flying by Earth, not very far away. But then, out of the blue sky, basically, came the other one, Chelyabinsk, from a totally different direction, unexpected, nobody knew about it, it was just there. So on that one day, in February 2013, 3 bodies happened to be in the same place in space, the Earth and the other 2 small objects, and one of them hit the Earth. Actually, it didn't even make it to the surface of the Earth. It still caused damage. So now we know from a lot of spy satellites, which is called government sensors here very nicely, that you see all these dots over the surface of the Earth. Those are explosions of meteorites over the Earth atmosphere. And this is from 1988 to 2022, not a very long period of time. So you see how many of those are actually happening. And so it's only a matter of time that a larger one comes down. So something people always ask me, if something like that hits the surface of the Earth, will it knock the Earth out of its orbit or something like that? No, absolutely not. Because the Earth is 13,000 kilometers in diameter, and a 1 kilometer or 2 kilometer, 10 kilometer object is so small mass-wise that when you look at, let's say, a beetle that hits the windshield of your car when you're driving along the road, will that knock you off the road? No, it won't either. And so it's very similar. So the Earth goes around, no problem. What? To understand these effects and phenomena, there's an international group that has declared through the United Nations now, 30th of June every year, the so-called Asteroid Day. This is something where museums, universities, and observatories around the world tell people about what happens in these impacts, or what danger asteroids can be, what happens with these big airbursts and so on and so forth. So that happens all over the world. But just to end up here, the last 3 slides or so, we need to know what's out there. And so very recently, look at the year 2000 here, what we knew about Earth crossing near-Earth asteroids. Only a few hundred were known back then. Now we know about 30,000. So astronomers are working hard to discover asteroids that could be dangerous to the Earth. And once we know where they are, can we do something about that? Well, maybe. Just last year, in September 2022, a small spacecraft called the DART mission, of course, DART is an arrow, but it also has the acronym of the Double Asteroid Redirection Test. It was a NASA spacecraft that hit a small asteroid about 150 meters across called Dimorphos, which is a little moon of another asteroid called Didymos, and to see what happens there. And in fact, it kind of didn't knock it out of its orbit, but it altered the orbit a little bit. And so what we see here was in white the original orbit, and after the impact, the new orbit. It's a little exaggerated, but basically that's what happened. And so we can do something about it. We just need to know it long in advance, to send out a spacecraft and maybe nudge one of these dangerous asteroids a little bit. And with that, I'd like to thank you for your attention. And now we can have a discussion. Okay?
Thank you very much, Christian. Great talk.
Wow, yes. Amazing presentation, Christian. Thank you very, very much. Álvaro, quer fazer alguma primeira pergunta? Eu tenho algumas.
Eu também tenho uma ou duas aqui para a gente começar esquentando. Posso fazer uma, você faz outra.
Vamos lá. Começa, por favor.
Okay, Christian. When we talk about the impact craters, a lot of people get curious about why there are some regions on Earth that have more concentration of impact craters than others. So if you could comment, and if you think there are regions that could get more impacts than other regions, or that's something completely different.
Well, in fact, if you remember some of my slides there, and let me see if I can share that again. There was, let me say present, share screen, and I share this one. And if I show you this diagram here again, it shows the small ones, the explosions in the Earth's atmosphere, which is measurements of something, what's coming down. And that is totally randomly distributed over the surface of the Earth. On the other hand, if we look at the, let me go back to this other slide here, the ones where we see how many craters do we know on the surface of the Earth. Where is that? Here. You see this one. This is the one you're referring to. Now that looks different. There's some areas where there are craters and some where there are not. And the reason, and let me just stop sharing here again, the reason, of course, has to do with the age of the rocks that are preserved on Earth. One, and the other place is how easy is it to find an impact crater. Now, if you look at the jungle, the Amazon or in Africa or so, then you won't see a crater very easily, but you'll see it much more easily in the desert. For example, in Australia or in the Sahara, you see it much more easily. And then the other thing is in South Africa or in Australia or in Northern Europe, there's a lot more craters than appear to be somewhere else. Well, because those are what we call old cratonic areas. And those are rocks, surface rocks that are maybe hundreds of millions to even a few billions of years old, whereas in other places on the Earth, they're much younger rocks. And so this explains why. So it's a preservation, basically, effect. They formed the same way everywhere else, but now after geological periods of times, there's not that much left over anymore.
Paulo, you may go ahead and ask the question.
Christian, please. By analyzing the impact craters, can we know which type of the impacting body was responsible? Was it an asteroid or a comet?
Okay, so comets we can almost exclude because comets are very, very rare. Now we know, as I showed you in the diagrams, we have thousands and thousands of asteroids that are in Earth-crossing orbits. Comets, in fact, we know none right now that is in an Earth-crossing orbit. So they are very rare. And so let's forget about comets. Let's look at asteroids. Asteroids have different compositions. Some of them are rich in iron meteorites, of course, and some of them are stony. And the way we can try to tell is only through the composition, some geochemical compositions. If we find a little bit of meteorite material mixed in impact melt rocks and glasses. Meteorites themselves on the surface of the Earth, they weather away, they erode relatively fast. So after a few hundreds of thousands of years, or even less, no meteorite fragment itself will be left. The only thing we have left is a little bit of meteoritic material that is mixed in with terrestrial material. Now the problem is that maybe you only have 0.5% of meteoritic material and 99.5% terrestrial material. So you need to get some geochemical methods that tell you not only that 0.5% is there, but also what is the composition. You can compare that maybe a little bit like if you put salt in your soup. You don't see it, but there are ways how to find out that there's salt.
Yeah, sure.
And it's the same with meteoritic material in impact losses.
Okay, thank you. Álvaro?
Yes, some non-experts usually look at Google Earth image and see round features and think they found a new impact crater. I think you mentioned something quite interesting, is that to demonstrate that a round feature is an impact structure or impact crater, you need some expert detective work. Perhaps you could go quickly through the steps after you find a round feature on an image. How can you really prove that that's an impact crater?
I always call this the curse of Google Earth. These days, everybody sends you photographs. I found an impact crater. It's just some round thing on a satellite image. And my answer is usually, have you looked at the geology of the region? Yeah, is there anything published? Yeah. I mean, I can't, from an image, from a photograph, one has to categorically state it is impossible to determine if it's an impact crater or not. A photograph can never tell you that, what it is, you know? So you actually have to go and look at the rocks. And some people may have done that before. And so for most places on Earth, there are geological descriptions. There are geological maps that tell you what it is. And in most cases, I would say in 99 out of 100 cases, it is not an impact crater. It is something else, because there are many other geological features. However, if you find something that makes you think maybe there is something that you can study in more detail, well, I said, what we have to do is first we have to get the rocks. Even in proven impact craters, you don't find sometimes evidence that it's an impact on the surface. So sometimes drill core samples are necessary. Then you need to go through it with large magnification microscopy and or geochemical methods. And there is not very many people and not most geology departments around the planet either at universities that have experts that know about how to do these analyses. So my recommendation is, first, you go through the geological record, you look what there is known, what there is published about these features, and then you make kind of a checklist. And if you think you found something interesting, try to get one of the very few impact experts around the world interested and see if they can take a look. Sometimes, I get pictures sent, and my usual answer is you can't tell anything from a picture. But the same with meteorites. People send you photographs of some black rocks. Is that a meteorite? Well, how do I know? I need to analyze it. So a photograph doesn't tell you anything. So people have to understand that photographs are useless in such a case. They may be interesting to arouse your interest, but they can never be proof or provide evidence.
Dr. Christian, please. The larger impact structure on the planet until now is the Vredefort on Africa, South Africa. What is the possibility and chance to finding another larger impact structure on the Earth? Is easy, is not so easy, because this obliteration that you tell us, what do you think about this? It's possible.
It's certainly possible. Yeah, you cannot say it's impossible, because just 30 years ago we found the Chicxulub structure, and that's a 200-kilometer structure, but you don't see it on the surface of the Earth, so it is hidden. So there is a chance that there is a large structure, or maybe part of one. From Vredefort, the actual structure is not there anymore. It's only a remnant. It's only a fraction of what there was.
Yes.
So it is possible that we find something, but let's say it won't be easy, because if it were easy, we would have already found it.
Yeah, for sure.
Okay. Yeah, and you must bear in mind that most of the Earth's surface is covered in water. So we might have a lot of unknown submarine impact craters that we still don't know about.
Well, actually, I'm not so sure about that because,
Why?
well, as you know, the surface of the ocean is a lot younger
It's
than
much
the surface of the continents. On the continents, we have some rocks that are maybe 3.5 billion years old. There is no ocean floor that is 3 billion years old. The oldest ocean floor that we know is on the order of 200 million years old. So now you can calculate how many impacts have happened during that time. Not that many. And the second important point is, in order to make an impact crater on the bottom of the ocean, you first have to displace a huge amount of water. And so you may have a very short-term impact structure, which is a nice hole in the ocean, but it closes up, and then you have tsunamis, and that was it. So you only the largest impacts make it to the surface of the ocean floor, and because the ocean floor changes all the time, if you look at the Atlantic wasn't there 130 million years ago. Geologically speaking, that is not that old. So that is the problem, that yes, there may be a few impact structures on the ocean floor, but not that many.
Okay. Álvaro, I have one question, Dr. Christian. How many impact structure around the world you have studied and researched? Is one question.
Or visited.
Yes.
Really, I don't have an up-to-date count, but
more or less.
I think I've studied something like 50 or 60 impact craters around the world.
Wow.
Maybe a little more. I've probably visited a lot, around 50. So,
amazing.
But I've been working on this for the last 40 years. So.
Congrats. I have another question. We have evidence of the impacts throughout the planet's geological and evolutionary history. We can say that asteroid impacts are an important mechanism for changing ecosystem on the planet. What do you think about this situation? Like you told about the Chicxulub, but we know that have a lot of impact. How can I say? You found it in Cretaceous, in Triassic, in all periods. What do you think about this?
Well, that's actually an interesting question, because shortly after the impact evidence was discovered for the Cretaceous tertiary boundary and the Chicxulub structure, a lot of people who never heard about impacts before suddenly were thinking, oh, all these extinctions, they all have to do with impacts. And that's not the case, because the only large extinction where we have evidence that there was a large impact is the Cretaceous tertiary boundary. Now, of course, impacts have happened, and they have influenced the climate and the biological evolution on Earth. But maybe I think we have to put things into relations. There's a lot of geological processes that go on Earth. There's a lot of volcanic eruptions. There's other things that change the climate on Earth and have changed it over a long time period. And impact is one of them. It is not the only, and it is maybe not even the most important geological process, but it is one of them. It did it in some cases. And where I think the problem is we don't have much geological record from them. But early on, in the early history of the Earth, maybe 3.5, 4 billion years ago, impacts were very, very important. And they did a lot of resurfacing and changing the surface of the Earth, because back then there were many larger bodies out there between the planets. They're all gone. They've all impacted. They're gone. So now it's the smaller ones that are left over. And so I'd say let's not exaggerate, and let's just be realistic and say impact is one of several large-scale processes that affects the evolution of life and climate and so on Earth, but it is not the only one.
Yes, wonderful. Thank you, thank you. Álvaro, please.
I think I've got most of my comments. Are there any questions from the participants?
Eu só tenho mais uma questão, na verdade, de agradecimento a ele. Dr. Christian, congratulations on the incredible collection of the meteorites and impactites in the Vienna Museum. Vienna Natural History Museum is amazing, in my opinion. Like Álvaro told, is one of the best, for sure. And what's your opinion about the impact material collection in the Vienna Museum, and why is not we cannot find in other museum good impact collection? Why? Including the most important, like I don't know. I don't want to speak about the other museum, but for sure, it's not the target of the museum impact material. But it's so important.
Yeah.
Why Vienna is one of the best have this target, and the other museum knows?
Yeah.
I don't understand it.
Well, I think partly it is a question of the people who have been curators and who are involved in these things. And in Vienna, we've had since basically the collections date back to the Imperial Natural Sciences collection, and even back in the 18th century when the collections were founded, meteorites were immediately included in the collection. And then at the beginning of the 19th century, there was a director of the whole natural sciences collection, a guy named Cradle von Schreibers. And Schreibers, who is now immortalized with the mineral schreibersite, which is common in iron meteorites especially.
Yes.
He was the director of that museum for something like, I think, 40 or 50 years or so, for a long, long time.
Oh, wow.
He started out actually as a zoologist and then became so interested in meteorites that he was really creating a huge collection at that time. And after him, there were people like Gustav Czermak and many others who were well known, who are well known in the science. Then just now in the 20th century, there was Gero Kurat, who was for like 30 years or so more, he was the director of the mineral and meteorite collections, and he was a meteorite researcher. So he helped a lot. I was director for 10 years of the whole museum, so I was, of course, in favor of the meteorite collection without neglecting the other collections. And then, so people, it's people, it's people have to be interested, and there's very few positions in museums too, so you have to, it's impossible to cover everything. But I'd say the large museums like the Smithsonian, also the London Museum, the Paris Museum, they all have large meteorite collections, and there are lots of people working on that. And occasionally you find people who are also interested in impacts. And so when I leave the university, I'll have to see when I retire where my impactite collection goes to. Probably will go to the museum because it should be preserved. It took a long time and many decades and a lot of work to collect it, and so it should be preserved with time. So it's people.
Yes, yes, I agree. But I visited the Royal Ontario Museum in Canada. I find an amazing meteorites collection, but just a few impact rocks in its position. I don't know why, because Canada, like USA, Australia, is one of the most important country that you can find several impact craters. For this reason, I don't know. For sure,
There are many other places in Canada that have impact rock collections at the Geological Survey, for example.
Yes,
so there are other places that have it. Doesn't have to be necessarily a museum, as long as people preserve it.
Yeah. What do you think about this, Álvaro? Your opinion?
I totally agree with Christian. I think it's people behind the curation that decides what type of samples they want. So if there are biologists interested in mammals or in birds, they'll probably go after those specimens. Whereas if there's a geologist interested in impact craters or meteorites, they'll probably try to get a good collection.
Yeah, it's correct. So now I think we can finish our amazing presentation and the amazing meeting. So, Dr. Christian, thank you so much. For me, it's a great honor and a pleasure to stay with you and my friend, Dr. Álvaro. Thank you very, very much. And Álvaro, muito obrigado por você estar aqui comigo e com o Dr. Christian. Muito obrigado por você ter intermediado também essa live. Foi realmente fantástico. Para mim, realmente uma grande alegria estar com vocês dois aqui. E como eu te disse, Álvaro, agora eu estou tipo álbum de figurinha, hein? Nós já temos você, o Dr. Uwe Remold, a doutora Natália Hauser, temos o Dr. Gordon Ozinski, agora o Dr. Christian KOEBERL, temos ainda a doutora Letícia e a doutora Grace, ou seja, eu acho que daqui a pouco, se tudo der certo o ano que vem, se eu conseguir reabrir um museu, eu quero fazer um grande evento, e se eu tiver bastante apoio, eu quero trazer todo mundo para fazer um grande evento de impacto, mas com essa visão de educação para a sociedade, que eu acho que falta muito. Álvaro, eu tenho feito algumas palestras, tenho feito alguma coisa sobre impacto, e tem gente ainda que não sabe que no Brasil tem crateras de impacto, Álvaro. Então, para a gente finalizar, eu gostaria que você falasse para o Christian fazer as suas considerações finais. Você também faz para a gente se despedir de todo mundo.
Christian, if you want to say a few final words, I'll say something in Portuguese and then you can close, right?
Ok.
Bom, de fato, eu sou testemunha do esforço enorme que o Paulo Mattioli tem feito para divulgar esse tema tão pouco conhecido, né, nas ciências, mesmo entre geólogos. A geologia de crateras de impacto, de processos de impacto, que é um tipo de processo geológico fascinante e muito pouco conhecido, ainda é pouquíssimo estudado. Então, esse esforço que o Paulo faz é muito importante, né, porque justamente ajuda a gente a divulgar esse trabalho de um número bastante restrito de cientistas aqui no Brasil, como mesmo citou. Então, eu agradeço a oportunidade aí e fico sempre à disposição na torcida do seu museu reabrir aí em breve. And I think Christian can make a few concluding remarks.
Well, first of all, I would like to thank you for inviting me to give this presentation. I hope it was of use and hope some people will see it. And impact craters, I'm sure Álvaro said something similar, are a fascinating topic to study. And we learn so much more, and every year there's something new that we learn. And if you look back, for example, just 40 years ago, people just freshly discovered not even the Chicxulub, but the evidence that there was an impact. And then another 10 years later only, the crater was discovered. So who knows what is hidden on the surface of the Earth. And I think this is a topic that will keep fascinating people, and it should attract a lot more scientists. And so I hope that the next generation will just be as engaged and fascinated by these topics as we have been. So thank you very much, and good night from Vienna.
Bom, pessoal, muito obrigado mais uma vez por estarem acompanhando aqui essa live maravilhosa, incrível aqui no canal do Museu Joias da Natureza. Assim eu me despeço dos meus amigos Dr. Christian e Dr. Álvaro. vocês tenham uma boa tarde, uma boa semana, e espero em breve a gente ter outro bate-papo, outra live bacana aí sobre assuntos tão incríveis da natureza, do planeta, enfim. Então, muito obrigado, Dr. Álvaro, muito obrigado, Dr. Christian, e até a próxima. Bye, bye, Dr. Christian. Bye, bye, Álvaro. Tchau, tchau.
Bye. Thank you.
Thank you very much.